introduction. So I would like to thank warmly the organizer of these workshops and to give me the opportunity to make a presentation of several projects we had in the group. I've changed a little bit the title of my presentation because I saw that many talks have been done from the beginning of the workshop on the energy harvesting. So I changed this word and introduced actuators. I will give you some details about the use of thin films materials, piezoelectric thin films materials, used for the actuation of mechanical structures for two kinds of applications. Haptic rendering, it's a wink to my colleague Frédéric, which is in the backside of the room, and another one concerning mixing of liquids used in microfluidics systems. So some words concerning our lab. So I'm co-leader of a group of research. We are around 25 persons here. Actually, we are working on the design of circuits, devices, and system integration. My co-leader is Laurent Fesquet. He's more involved in the microelectronic design of circuits using asynchronous approaches. TIMA Laboratory is a fabless laboratory. TIMA stands for Techniques of Informatics and Microelectronics for Integrated System Architecture. So we did a lot of kind of design of circuits using advanced technologies coming from foundries, namely ST Microelectronics in Grenoble. So 2 words about the group. So we have a group working on digital circuits using asynchronous approaches. This group is strongly involved in the design of ultra-low power circuits necessary for autonomous systems. And in the other side, I'm the head of this part of the group. We are working on the design of MEMS and NEMS devices, and we started a long time ago. So today I will make you an overview of several projects on MEMS for energy harvesting using microfabrication techniques used in microelectronics, and I will give you also some details about an application of energy harvesting for an implant. So the outline of my presentation is split in 4 parts. At the beginning I will speak about piezoelectric microscale devices for energy harvesting. This work started a long time ago in 2003, 2004 with several PhD students. Afterwards I would present the results we obtained changing our strategy. We moved from MEMS technology to ceramics and thinning of ceramics in order to provide enough energy for an implant. I will make just a short presentation of work of a young colleague in the United States speaking about ultrasonic power transfer, because it's a very nice link between these 2 kinds of technologies. We can see MEMS technology with ceramics, and in order to make this ultrasonic power transfer. And finally, I will explain 1 or 2 examples concerning piezoelectric actuators using thin films. So at the beginning, concerning the first part, I will give you the context quickly, because I think you know exactly what is energy harvesting. Afterwards, I move to the modeling and design in order to give you some guidelines we have used in the past, and many groups are actually using almost the same approaches. Some detail about the fabrication process developed long time ago with Femto-ST and other colleagues in Europe in the framework of an European project, VIBES project. And finally, I will speak about the electromechanical characterization of the device. So the aim of our work was to provide enough energy to power autonomous sensors using wireless sensor networks, and also to provide enough energy for implants. So the range of energy of or power. I prefer to speak about energy, but anyway, many people are also speaking about power, is very, very low compared to the energy or power necessary for this kind of macro systems. So if you look at a watch, for example, you need only 1 microwatt. So a long time ago, at the beginning of the 2002, 2003, when we started this project, we faced many questions concerning what kind of transduction principle and what kind of energy available in the environment was sufficient for providing enough energy for this kind of autonomous sensors. And it's clear that many people were already on the outdoor solar energy, indoor solar energy. Many players were there, and we decided to work on energy coming from mechanical movement, mechanical strain, mechanical vibration, and we focused on this kind of energy. The power density or the energy density was clearly high enough in order to transfer this kind of energy, mechanical energy, into electricity, thanks to a transduction effect. Among the transduction effects, there is just one detail. Concerning the energy, we focus more on the vibration. We studied also some deformable structure with Claire, with another kind of transduction effect. This is based on electrostatic effect. So today I will speak about the piezoelectric transduction. And concerning the vibration, you can see from this spectra that you can have for human body very low resonant frequency, and the spectral density, the power spectral density is very close to 10, is close to 10 Hertz, in this case. And in this case, you have broad energy available up to 200 to 600 Hertz. So now the question was concerns the choice of the transduction principle used for converting the mechanical energy, the vibrations, into electricity. So I reported here the pioneering work made by Shadrandi to explain what is the best one in the best case, etc., etc., etc. And we use this table in order to convince ourselves to choose the piezoelectric transduction effect. But we have also worked on the electrostatic with some PhD students in the CEALT, namely Ghislain Despès. And we focused on the piezoelectric because in 2003 and 2004, only the work of Shadrandi was presented in the literature using microscale devices. So I decided to go in this project, trying to push the MEMS technology in order to convert the mechanical energy into electricity with the MEMS technology available in the lab. So when we decided to work on piezoelectric transduction principle, the question was, are we able to understand what are the key parameters involved in this transduction effect? So if we summarize in this slide typically the two kinds of transduction used in the transfer of mechanical energy into electricity, the free mode, where you have the force or the stress applied to the piezoelectric material parallel to the polarization vector, or here you have a transverse effect of the force. It's clear that this kind of transduction effect is used typically in accelerometers. Okay, accelerometer where we have a piece of piezoelectric material and the mass on top of it, And but this model is very easy to describe because you can use only 1D description of the equations. And in the other hand, you have a different approach based on the 3-1 mode. And in this case, we can use some clamped beam with a mass. The mass, I will explain the role of the mass. The mass is here just for tuning the resonant frequency of the device according to the input energy available in the in the environment. So the first step of our work was to try to model these two kinds of structure in order to understand what is the role of the material properties on the energy scavenged by the system. So if you look at this table, which is a well-known table with some typical parameters concerning the piezoelectric properties of the materials, we can have here the permittivity, the D33, the coupling factor, the QM, which is the quality factor, the mechanical quality factor. It's clear that you have strongly coupled material like the PZT alloys and the ceramics here, and you have polymers with poor coupling, aluminum nitride, which is an interesting material because you can deposit it by sputtering techniques, for example. And we put this kind of parameters in our model, and we added also some data not available here in this table, some losses concerning dielectric losses and viscous damping and so on. And just on playing on these parameters, we started with this kind of basic model, and we added, for example, here the viscous damping, structural damping, also the tangent delta, which is the ratio of the imaginary part of the permittivity of the dielectric material, piezoelectric material in this case, over the real part of the imaginary, real part of the permittivity. And you have also introduced the electric load, which gives you the opportunity to transfer the mechanical energy and to an electrical in the electrical domain. And we have introduced all these parameters. Okay, the electrical load, the electric losses, structural losses, viscous losses, and so on. And making the balance of the forces concerning this kind of structure, we were able to write the output voltage times the output voltage, where we take in account all the physical parameters of presented here, and we can write this equation in the Laplace domain. And we can also obtain the power output, and we found that this power output can be written in this way. It's the ratio of the mass times the acceleration to the power 2 divided by the natural resonant frequency, or angular frequency here to the square. This result was very interesting because in this case, compared to the electromagnetic one, you can see that you can use piezoelectric materials even at very low frequency, which is not the case for the electromagnetic. Electromagnetic, you can use them, but the efficiency is the power is written in a different way, and especially for electromagnetic, you have very low voltages at a low frequency, which is not the case for us. Okay. So this is why we were convinced to use the piezoelectric transduction effect instead of electromagnetic. So thanks to this model, we were able to plot some important curves: the displacement, the power versus the normalized frequency versus the value of the load, etc., etc. And this is the same case for the power. And we were able to show that in this case we have two peaks: the resonance for omega equal 1 and anti-resonance, and this is due because the material used in this simulation is a PZT, is a strongly coupled material. So you have different kind of you have two kind of let me say two kind of resonances. You have the resonance and the anti-resonance, and we can obtain almost the same power output for the device. So we have also plot the power versus the resistance, and also versus the effective coefficient, coupling coefficient. And even in this case, we were able to find the optimal configuration for the extraction of the power coming from the energy harvester. So we can find, for instance, the critical coupling, for example, at the resonance anti-resonance. Okay, so we have found finally that if we come back to this 3D and we make a 2D plot here, and we report here the power versus the effective coupling factor, it's clear that the viscous damping ratio plays a different role on the Z1 zone or Z2 zone. Okay, so this kind of conclusion were very interesting in order to understand how to use the device at the optimal parameters. Afterwards we have compared the materials, and this curve is very interesting because we compared let me say a very good piezoelectric material, a PZT, if you look at the coupling factor, okay, with a high QM and a tangent delta equal to 0.5%, and this aluminum nitride. And we found that the two peaks are very close together for aluminum nitride because the material is not very well coupled, and PZT are far for the resonance and the resonance. It's more evident for this kind of material, which is more coupled. But we can see that we are, concerning the power, we are very close between the aluminum nitride and the PZT. We have only a factor 2, which is not very easy and easy to understand if you look only at these parameters. Okay? So we focused our attention on this kind of material because aluminum nitride is easy to deposit it by CMOS technology like sputtering technology, PZT by sol gel technology and processes. And we have shown during this first part of the modeling that the power was proportional to the mass, to the square of the acceleration, and inversely proportional to the square of the resonance frequency. It's one of the main results we obtained. For strongly coupled system, we found two maxima with the value of the resistive load, the resonance and the anti-resonance. And the power dissipated into a resistive load increased with the coupling factor up to a critical value. And after that, you have a plateau, and it means that you have no effect of the coupling, effective coupling factor. These values are very interesting to have to keep in mind in order to make the devices optimal devices. Finally, for strongly coupled system, the increase of the quality factor plays a more important role than the coupling factor. Okay, so we did this first work, and afterwards we started the modeling of cantilever beam. So in the literature in 2003-04, the models proposed in the literature are few, and few of them were devoted to the energy scavenging. They were typically simplistic, without no losses. The beam were straight beams with sometimes no mass on the tip. So the models were not adapted to MEMS structures because In the literature, the models were based on the symmetric B-morphs, for example, which is absolutely not the case in MEMS devices. You have a non-symmetric structure with the silicon substrate, for example, on top of which we can put some thin film, piezoelectric thin films. And especially, they don't take into account the losses. So thanks to this approach, we started a more complex model, which is representative of a MEMS device. Okay. Concerning the boundary condition, we have introduced a big mass on the tip of the device. The model used is a Euler-Bernoulli model, so it means that it is representative of a device excited in the linear regime for low deformations and so on. And it's a straight beam also. The beam is composed by two layers, piezoelectric and the silicon material are used in our case. And we have introduced a new thing, a rotating inertia of the mass, because you need a big mass on the tip in order to decrease drastically the resonant frequency. And we have also introduced the losses as we did for the 1D model presented before, the dielectric, the viscous damping, and the structural damping. All right. So the two coupled differential equations were more complicated than before, with many terms reported here. All the equations are well explained in the PhD of one of my former students, Marcin Mazenki, and David told me that there is a small mistake in one line of the. Thank you very much. We have to discuss about that, but I'm not sure that there is the mistake. But anyway, and you can see that here you have the coupling between the mechanical variables and the electrical variables. And here you have the inertia, rotation inertia introduced here, and the acceleration applied to the device. This kind of model was solved using analytical equations by numerical simulation using Maple or MATLAB, as you like. And we compared these results with finite element analysis using ANSYS. All right? So we assume that ANSYS gives us the right results, and we compare the two models, the simple model without the rotation of the mass, and the more complicated, more refined model with this phenomenon. And I'm sorry, some pictures are written in French. So the refined model raffiné, is the model with the rotation of the mass around the axis, which is close to the clamping of the mass with the beam, straight beam. And the simple model is the model without this phenomena. So we can see that you have, and the percentage here is the comparison between the analytical modeling and the finite element analysis. So you can see that we make a big mistake here when we increase the dimension of the mass. It's clear that more the mass is bigger, and you have a bigger rotation of your mass at the clamping part between the mass and the beam. And what else? But if you can take into account the refined model, we are very close to the finite element results. This is very important for making the design of the final structure for a given application. So even in this case, we have made several comparisons between finite element analysis and our models, introducing different parameters. Viscous damping. This is the viscous damping ratio effect. So increasing this viscous damping ratio, you kill definitely the resonances, the resonance and the anti-resonance. We found a quite good quite good agreement between the analytical model and the finite element model. We have also introduced some variation like this one, the effect of the resistant load versus the normalized frequency. You can see here that lower is the damping factor, lower is the value of the resistance to be plugged to the device in order to scavenge efficiently the the electrical energy coming from the piezoelectric material, etc. So this model was also powerful in order to understand the effect of the piezoelectric layer on top of your substrate, which is sometimes silicon, sometimes metallic foils, like the technology developed by a colleague of us in Taiwan. Okay, they make a PZT on top of metallic foils, and if you take into account all the mechanical parameters, dielectric and the viscous damping, it's clear that you can find an optimum. This is the case here when you look at the variation of the power versus the resistance connected to the device, and versus this C, which is the ratio of the piezoelectric layer, height of the thickness of the layer, over the thickness of the substrate. So it's clear that in our case, you have the quality factor of the piezoelectric material, which is very low compared to the to the silicon. And in this case, if we decrease the thickness of the piezoelectric layer, we increase the power. It's sure that if you replace the substrate by metal, the result is completely different. So you have to take all these things in mind. We choose the material, and I will speak about a figure of merit just after this slide. But you have to understand how to introduce the material with the structure, because the structure plays a very important role. Another very interesting thing is the influence of the electrical properties of the piezoelectric materials used for the transduction effect. If you look at the aluminum nitride and the PZT, and we make a closed loop on the power, we have shown before that we have almost the same power with these two kinds of materials. But for the same amount of power obtained, due to the fact that the dielectrical permittivity of aluminum nitride is very low compared to the PZT, it means that your capacitance of aluminum nitride is very low. So it means that your output voltage is very high. Well, you say, okay, but it's very interesting to have if you have the same power, it's okay. But it's not really the case, because you have to think to your friends working on the electronic circuits. Okay, if you provide 100 microwatt, but at 100 millivolt or 50 millivolt, which is the case in the electromagnetic transduction, sometimes it's clear that it is difficult to rectify the signals and so on. So sometimes it's better to have different materials with a lower power output, but with enough voltage in order to start the electrical circuit for the AC/DC and DC/DC transduction. So, in conclusion of this first part, it's clear that at the end of the 2010, a lot of figures of merit were published in the literature. Among them, the one proposed by my PhD student for the piezoelectric devices, Philippe Basset, colleague of us, for the electrostatic one. The very popular in the energy harvesting activity is the figure of merit proposed by Paul Mitchison from Imperial College, and for this free figure of merit, we take into account the device. And we have also the picture of merit of Professor Pierre here is more focused on the material properties. So this is very interesting to have in mind that thanks to this kind of figure of merit, you can choose your material. But the work is not finished. You have to take into account also what kind of device resonate. In this case, you are just speaking about a resonating system. It's a pure, let me say, seismic devices, like accelerometers. Okay, so in this case, you have to be careful about the things we have to take into account for the best, a good, an optimized design. So sorry. Now I will speak about the fabrication process. So we fabricated several devices, and we started with the target application during this project, European project, in 2004 and 5 and 6. He finished in at the end of 2006. It was the, let me say, to scavenge energy available on a machine tool from this company, SkyMill, in order to provide some information to the technicians. The size of generator, we decided to design the devices with this this volume. This is the maximum of the volume for the generator. Typically, the resonance frequency was, this is the variation of the amplitude of displacement at a given point of the machine versus the frequency. So you have peaks at close to 1 kilohertz to 1,800 kilohertz, and so on. And the excitation acceleration was very high due to the movement of the mechanical parts, so up to 25 G. Okay? So taking all these parameters in mind, we started the fabrication of MEMS devices. We are convinced at that moment that MEMS techniques were the best techniques to employ for making the device. So we started by SOI substrate and two kinds of piezoelectric material, aluminum nitride and PZT. I will give you some details about that. So we started with SOI substrate. At that moment, the substrate was extremely expensive. So, okay, but anyway, the aluminum nitride was provided by MEMSCAP in the United States. For the PZT, the process was done by the group of Paul Murat in EPFL. So afterwards, you have here all the steps for the fabrication of the piezoelectric layer located at the clamped part of the beam. So this is a SEM view of this step. Afterwards, we make the deep reactive ion etching in order to release the seismic mass. Okay, this is another picture concerning the process, and finally we make the releasing of the device using HF acid in order to release the cantilever beam here with the mass. This is one picture of the devices using aluminum nitride. You can see here the under etch of the mass during the deep reactive ion etching step of the process. This is a close-up view of the PZT fabricated at the EPFL. A very long process. Okay, each layer is close to 100 nanometers or sometimes less. With the recrystallization, it took a long time, but PZT is a very interesting material because it's a ferroelectric one, and it gives us more degrees of freedom in the design of the final device. I will explain to you what we did at the moment. This is the device finally fabricated in a PFL. Just a comment concerning the clamping part. Even at this moment, 15 years ago, we started on the design of reliable structures. Using this filleted clamping part, you can homogenize the stress in the piezoelectric layer along the length of the beam. You decrease the concentration of the stress on this part of the device, just on playing on the curvature of this filleted part of the device. So we started, after the fabrication, the electromechanical characterization of the devices with a full automated bench setup, with the shaker, with the automatic variation of the load in order to plot the curves, power versus load, etc., etc., etc. We have also put on top of the shaker a vacuum chamber in order to see the effect of the viscous damping on the performances of the device. Okay, and we have obtained these results for aluminum nitride, the resonance, the linear behavior of the device, and increasing the acceleration, the hardening of the device, the non-linear behavior of our system. Concerning the aluminum nitride, you have only one peak. The resonance and the anti-resonance are merged together, so you have a wide band here, which is not the case for the PZT, for example. And here we report the variation of the power output versus acceleration and the voltage on the optimal load, which was in this case 650 kilo. Okay, so with the 4G we were able to obtain up to 2 microwatt, which was among the best results published at the moment. If we look at now at the results obtained on the PZT devices, here you can see the power versus frequency for different electrical loads, and you can see the anti-resonance and the resonance. This is clearly reported here. You have two peaks. That means you can scavenge energy at the resonance or anti-resonance. And I've put some curves concerning here the variation of the output voltage and power at the resonance and the anti-resonance. So you can see that you are very close concerning the anti-resonance. You are a little bit less than 1 microwatt at the 2G. Finally, okay. So now if we go to the PZT layer. PZT layer is extremely interesting because it's a ferroelectric material. So it means that thanks to interdigited electrodes, we are able to put the polarization field in the plane of the thin films. That it means that you bend your cantilever beam, you are exciting the free mode. And then you have a higher coupling effect, and then you have better results than the previous one. So, thanks to this idea, we replaced the two electrodes by interdigitated electrodes on top of the device and on the bottom. Top and bottom, all right? Why? In order to have all the material excited and polarized in the plane. So we did that thanks to the technologies and thanks to the thin films made at the EPFL. So I will explain everything here by these sentences. Playing on the distance between the two electrodes, you can play on the voltage to be applied in order to obtain the good value of the field, which is able to change your polarization from the perpendicular position between the two electrodes to the polarization in plane. All right? So here, some results concerning this case. At the anti-resonance, at low frequency, and this device was resonating at lower frequency due to the fact that the device, we have not under edge of the mass, which was not the case for aluminum nitride. Okay, the targeted frequency was close to 1 kilohertz. Okay, in this case, we have very nice definition of the mass, so we are very close to the 800 or 900 hertz. So it's clear that for 2G, instead of 1 microwatt, you obtain 1.4 microwatt. It's close to 30% more than the previous example, due to the fact that you are using the key free instead of key free 1 coupling factor. Okay. So at the end of the project, we presented the first system in package, including the MEMS generator and a circuit, a voltage multiplier circuit. Is a very basic one using diodes, and we were able to rectify the signal provided by the device. So we published it on these results. We demonstrated that thanks to this device, we were able to provide enough energy to this autonomous sensor. Sorry, you have the board here with the wireless system, supercapacitor, and here you have your generator. Putting everything on top of the shaker, we succeed in charging the supercapacitor and transmitting the information. We measured the temperature to a PC. Okay, this is the main results we obtained long time ago, in 2007. Okay, so as I mentioned at the beginning of my presentation, it's clear that a lot of vibration are lower than 1 kilohertz. So we decided to face this challenge. Okay, at the end of the 2007 and 2008, we have shown that it was possible to create this kind of microgenerators. Fang, 1 or 2 years before, did the same with the PZT and the nickel deposited by electroplating on top of a beam, obtained a bigger value due to the fact that the mass is bigger. Okay, and we decided to design generators working at lower resonant frequency. We did that using exactly the same rules, CMOS technology, etc., etc., etc. We have just played on the parameters of the generator. Okay, so the mass is a little bit bigger. You can see here the filleted structures. Okay, in order to provide an homogeneous stress of the piezoelectric material all along the beam. We have made not only cantilever beams but also clamped beams in order to see bistable structures. This is a close-up view of the devices. Okay, these are typically the results you obtain. So we have shown that it is possible to go to the very low frequency. We did also, after this project, this PhD, device is resonating at 100 Hz, but it's more and more complicated to use them, and I will explain why. In fact, these resonators has a very high Q factor. Okay, and when you excite them, or even at low acceleration values, you have you obtain less power. This is due to the fact that you are working in the nonlinear regime of the device, and this nonlinear regime decreases drastically the efficiency of the scavenger. So the nonlinear effect is a problem sometimes, and it can be seen as I report here the variation of the output voltage versus the frequency. You can see that only at 10 millig you are still linear, or 25 millig, but you have a stiffening of the structure at 50 millig, which is nice, but it's a real problem to face. And you have a shift, and sometimes it is interesting to use this kind of nonlinear effect in order to follow the variation of the excitation of your device. I will explain that just after this curve. Here we report the effect of the vacuum. Just playing on the vacuum on your device, you can double the power. Okay, this is reported here. Here the displacement is just limited by the packaging, because you have a so big amplitude that you touch the packaging, okay, during the vibration, even at very low excitation. As I mentioned before, figures of merit are very interesting in order to compare the work we did to the work performed by different groups. And we report here some results obtained by Maxime Defosseux on different kind of structures. Sorry, voilà. So I will finish this first part of the talk. So up to now, this approach is used by several research groups. There are many people working on this kind of approach: thin films, aluminum nitride, KNN, on piezoelectric, on silicon substrate. Actually, different groups are optimizing the performances of aluminum nitride, for example, by topping it by scandium. Some of them are working on leadless materials. It is, I think, very interesting to change the approach in order to propel this kind of generator by changing the substrate, because SOI is still expensive. Then if you have another low-cost substrate, it is better, metallic foils, polymers. And finally, some groups are working also on the optimization of reliability and robustness of these tiny devices. So now I move to the second part of the presentation. So I show that MEMS devices at the micro scale can provide 2, 3, 4 microwatts and maybe more. Some groups in the United States shown better results. Now, as I mentioned before, this is the, let's say the pioneering work of Chadrandi, 2004, his work, his books, and etc., etc. And we did the first prototypes in 2007 with Marcin, and afterwards with Maxime in 2011. But however, if we look at the resonant frequency, it's clear that for some application you are lower than 200 Hertz. So we decided to study this kind of generator. This the project was the Heartbeat Scavenger. The project, the aim of the project was to replace conventional pacemakers with the lead here by a beam screwed inside the ventricles, and inside this capsule we imagine to put energy harvester. And among the transduction effects, some of our colleagues proposed some devices using the electrostatic transduction effect, and we focused on piezoelectric. The idea is absolutely not new. 50 years ago, a group of inventors proposed this approach to put a piezoelectric generator inside a capsule. In 2013, St. Jude's proposed this kind of device, but instead of a generator, they put some batteries. So the idea was, are we able to replace the batteries inside this device by a generator in order to provide the energy to the leadless pacemaker? So we faced several issues, because if you look at the specification given by the project leader, which was a company involved in the design and fabrication of this kind of things, they told us that typically the frequency content of the vibration source is between 10 and 25 hertz, which is 10 times lower than the last results I show you made by MEMS. All right. What else? The capsule volume is with a given aspect ratio, a given length, a radius of 6 millimeters, and the required energy is at least 5 microjoule, but if you can provide a higher value, it's better. So we are quite far from the values proposed just before on the resonant structures. So with all these things in mind, this is typically what we schematics of the device. You have here the cantilever beam with the mass, etc., the electronics and the electrodes and so on. So we decided to make a model. Okay. So the idea was to use the work performed by the group 50 years ago to put a cantilever beam inside the capsule. So we started with a cantilever beam with a symmetric system with 2 piezoelectric layers in order to provide more energy for a given deformation, okay, with a seismic mass, even for making the tuning of our devices to the spectral density, power spectral density of the system. So we started, first of all, with the study of available energy. So this is typically a transient signal recorded in the heart with accelerometer of a patient or measured in the heart of an animal. So this is the heartbeat waveform. So using the FFT and some signal processing, we were able to see the power spectral density. And afterwards, we put an analytical model. This is a Simulink model. And thanks to this model, we were able to calculate the RMS voltage, the mean power, but also the displacement amplitude of the device, because you have a displacement in a given volume, and we have no contact of the mass with the capsule because we can destroy the structure. So thanks to this model, and thanks to the database provided by our partners, we were able to identify the optimal scavenger dimensions. We have also made some fundamental validation of the analytic model to be sure that we target the best value during the optimization. So, in order to give an answer to these specifications coming from the project leader, the frequency of the volume and the energy, we can see that the frequency and volume tell tell us that the piezoelectric layer must be not too thick, because if you are too thick, you are resonating at high frequency, okay, and the volume is only completely occupied by the device. But if you need enough energy, the piezoelectric layers must be not so thin, because thinner is the layer, less energy is provided for a given kind of deformation of your material. So we obtain this kind of value for the thicknesses of the piezoelectric layers. It's a 50-50 PZT bimorph. Okay? So if you look at these parameters and we take into account this picture coming from the literature, interesting paper, it is clear that you have two approaches. You have the previous one, a bottom-up approach, the thin films, and we try to increase the thickness. And you have also the opposite one, the bottom-up, the top-down, sorry, top-down approach. You start from bulky ceramics, and you thin the bulky ceramics in order to go to the targeted value. So you have a black window concerning the fabrication. And I think some answers are coming from the group from Femto now. During this work, we propose the thinning of PZT substrate. Okay, I will go more in the details of the process. So I will show you that the choice of the ceramics is a key point of for the process, because if you go to the dealer and you take a standard ceramic, you have many pores inside the PZT ceramic, and then during the thinning of the material, these small pores can make a short circuit between the two electrodes. So this is a very important thing to have in mind. So this is, for example, high density material. The pores are very here is a high density, is the standard. Here you have a grain, for example, which is not the case here. So when you make the grinding and lapping, you have a very flat surface without any short circuit, and it is very important to obtain this kind of ceramics. Okay, so some details concerning the structure. So we have completely forget the silicon. So now we start with ceramics. We keep a piece of metallic foil. We glue together. We have a bonding of the ceramics. Afterwards, we have the thinning of the first ceramic. We did the same for the second one. The electrode plating, the pulling of the two ceramics, and finally we obtained the material, the stack. So here we have performed this process with a company, French company, located in Tours, Vermont. So here you have a bimorph, a symmetric bimorph. Here you have a unimorph. You have a 75 micron steel substrate and a 50 micron PZT layer. See, this is the first prototype we used in 2013, and after this processes, we started the characterizations. So concerning the characterization, the very interesting thing is to measure the impedance, which gives you some information concerning the coupling of your material, etc., etc. So we obtain some values, and after that, we put the device on the shaker, and we can see here, for example, the device without the tip, without the mass, resonating at 86 Hertz. When you put the mass 1.5 G, you decrease the frequency, and then you go inside the spectral, energy, power spectral density, But when you put the mass, the coupling, effective coupling is decreased, the two peaks are merged, etc., etc. You can see all the parameters here. It's clear that in this case you have 3 microwatts instead of 0.65 microwatts. So you increase by 5 times the number of microwatts. So even in this case, figure of merit is very important. And we were here after this work, and thanks to this work, to these results, this company is actually working on the commercialization of this kind of microgenerators for wireless sensor wireless sensors. So here you can see the bench setup, okay, and we use some waveforms merged on the heart of a patient, and here you have the electrical results. And this curve is very interesting because, as I mentioned before, you have the mean power versus the voltage, which is it's not power is one of the key parameters, but also the voltage. So we obtain between 4 and 12 microwatts at 3D, which is in line with the power requirements of this device. I will speak now about the integration of the microgenerator. So this work was done in another project after the first one. This is the laureate, and Elie Lefebvre was also involved in this project. So the integration of the generator was performed by this company in Tours, Vermont, and this is typically some tests made in vitro and in vivo. So this is a result. This is the device vibrating inside the heart of the pig. And some words now, because we speak a lot about energy harvesting. Okay. But energy harvesting for what? For replacing batteries. That it means that when you try to scavenge energy and to transform electricity, is to replace batteries. That means that your generators must work at least 15 or 20 years. Okay, especially if you may put it in implants. So during this project, the laureate project, our team were involved in the design of reliable structures. So we played a lot on the design of the clamped part in order to reduce the stress at the clamped part and to uniformize the stress along the beam, okay, for a given amount of power. So thanks to some techniques, we were able to reduce drastically the stress here at the clamping part without a big change on the output power. So this part was patented, a big work was done by the group of Elie at C2N. This is a rapid view of the bench setup they performed with his team in order to measure the activity of the generator. And if I don't so actually the device is still working, I think. It's 1.4 billion cycles, you said that last time, so it means that more than 15 years operation. Years of operation. Okay, so I will finish with this part. So now, some words because time is running. Okay, so I will move to the last part of the presentation concerning the actuators. And devices made with thin film actuators. So I will speak about haptic devices, only 1 or 2 slides. So the idea is to introduce a haptic rendering on flat surfaces like smartphones, tablets, in order to have a rendering of the surface, okay, smooth surface or not. So the idea came from the colleague from the 2EP. Okay, they patented it. The idea is to modulate the friction between the finger and the vibrating surface. So the idea was to excite the surface. Okay, so Fred is there, is one of the inventors of the structure. So they did that with big actuators, ceramics, and in the framework of a project where we work together, the work we did is the introduction of thin films instead of bulky ceramics. Okay, so the idea here is reported in this slide. When you apply the voltage to your piezoelectric layer, I think. So when you apply the voltage to your to the actuators, you create a lambda wave mode, antisymmetric lambda wave mode. With typically 1 micron vertical displacement on top of the substrate, with this kind of value for the excitation. The excitation must be higher than 25 kilohertz, because if it's less, you can hear the vibration. Okay, you create a loudspeaker. This is an old picture because things are moving a lot. This is the idea used at the beginning of the project 6 years ago now. So the work we did is to use the aluminum nitride stack used for making bulk acoustic wave resonators, okay, and to use them as actuators to create the lambda wave mode on top of this big surface of glass. And we have shown during the PhD of François that aluminum nitride was not so bad as a candidate, because it presents low losses, low dielectric losses, low mechanical losses compared to the PZT thin layers made by the colleagues. Moreover, there is a very important thing concerning aluminum nitride. The aluminum nitride is transparent, so in the next in the future, the idea is to make a mapping of all the surface with this kind of electrodes. If we succeed in the fabrication of transparent electrodes, okay, this is not a dream. People in Luxembourg did it using PZT technologies, so it is possible to make this kind of things. Okay, so this is typically this is typical results measured with a vibrometer at resonant frequency. The measurement. This is the displacement, the power used for the excitation of the modes, etc., etc. And we have also shown that we need less than 100 volt for the excitation of the modes. So it means that aluminum nitride is not so bad for making some actuators, and even for making the displacement of very big slabs compared to very teeny devices like the previous one, right? So another example, and I will finish my presentation. For this project, we used the technology developed by the CEOALITY for aluminum nitride. In the next one, we have used some, it's a work we did in collaboration with our colleagues from Brescia in Italy, the group of Marco Ferrari and Vittorio Ferrari, also known for their work in energy harvesting. In this case, we have designed some actuators for mixing liquids with nanoparticles, and the device was performed using MEMS cap technology. Okay, MEMS cap technology is a foundry. I'm sorry, the video is not working, so we were able to have a mixer, and we can have a rotation clockwise and counterclockwise just by applying the voltage on the interdigitated layers. The piezoelectric layer is, in this case, aluminum nitride 2. Correct? So in conclusion, we have shown that CMOS compatible technologies are interesting technology for creating autonomous sensors. We have developed a new piezoelectric MEMS for PZT ceramics, able to supply an implant. Actually, the perspectives concern long-term reliability of the materials and devices, the design of new structures to address the problem of multidirectional excitation of inertial scavengers, which is a very big problem. If you cantilever beam, you have 1D, it's clear. Concerning the actuators, you have shown that piezoelectric thin films can be used efficiently as actuators, and the new challenge concerns the deposition of transparent piezoelectric materials on top of transparent substrate. I will finish with the miscellaneous of things concerning piezoelectric layers. We did also energy harvester with Polymuralt. It's a bimorph of aluminum nitride and aluminium with a pre-stress. And thanks to a variation of temperature, you can buckle the system from one position to another one, and then you can obtain a signal. But the amount of power energy is so low that it is not a so efficient converter, but it could be used for as a sensor, as an event-based sensor. So you may imagine that the temperature is increasing. The threshold is obtained by the design of your structure, by just tuning the stress inside the material during the process. Okay, so you have a deformed structure. And then when you go through the thermal threshold, you have a buckling of the device, and then you have the signal. So you have the all-in-one. It means that you have a signal which is triggered by the variation of temperature. I didn't speak today about another subject concerning polymers, and more particularly piezoelectric. This is actually a very interesting thing we are doing with colleagues of us in Grenoble. Many people, especially Alper Erturk, is working on piezoelectric on foams. We did some interesting things on regular distribution of cavities in polymers made by design, and just changing the periodicity of the cavities, the dimensions, etc., you can play on the piezoelectric coefficients, on the mechanical properties, etc. These are typically the values we have obtained and published. All this work has been done thanks to a great number of collaboration with colleagues from different laboratories and also from companies. And I would like to thank you again for your attention. And the last, we have propelled all the work through startups. MEMSCAP was the first, and the other one are on integrated circuit, urinary sphincters. It's an implant, completely automated, and it's an artificial one. Hap2U is for haptic rendering. And finally, the how I take is more involved in the design of artificial intelligent devices and circuits. Okay, thank you very much.